Very nice. So I'm getting some different answers. Oh, okay. Very nice. Okay. So Melinda said the top one has no black and white, whereas the others all have black and white. Someone else said the top one is the only one that uses triangles. Okay. So somebody else said that the one on the bottom right is the only one that's based off an animal, or you could say it's the only one that's not using polygons for its sides. I heard that this top one, it doesn't rotate or change positions, like it's the grid, the black and white there would be the same. So, okay. Other thoughts or ideas that you guys didn't submit there? This is the only one that uses different shapes. I don't know if we said that. Okay, so it uses some squares and some rectangles, whereas the rest are all a single shape, just in different colors. Okay, so we're doing tessellations in geometry right now, and so I found these different tessellations, and I thought, these are kind of worth looking at and worth sharing. That tessellations can be a lot of fun. Okay, so let's jump straight into it. Let's talk about the 5 key points of the graph of cosecant, and let's get its vertical asymptotes, domain and range, and period of the parent function. Okay. So this is, I have to tell you, this is one of my mathematical most favorite things in the world, okay? So we know that cosecant is the reciprocal of sine. And what you're going to see is that just like reciprocal is the flip of the fraction, this graph is a flip of the graph. And I love that. I think it's super awesome and cool. Okay, and so Mr. B already kind of showed you guys that in the video notes. If you haven't watched him, go back and watch it. So if we graph the parent function of sine, which starts at the midline at 0, has a midline of 0. Okay, it starts at the midline, then maximum, then midline, then minimum, then midline. Okay, and it goes from 0 to 2 pi, has a period of 2 pi. Okay, so if I do that with a dashed line, because that's not the graph of cosecant, it's the graph that's going to help us get the graph of cosecant. So that's our sine's parent function. That's one cycle of the sine's parent function. Okay. And we're going to graph that with a dashed line every time we want to graph cosecant. And then we're going to flip the graph just like we would flip the fraction. So remember, when we're at 0, 0 over, so if we write that as a fraction, we could turn 0 into a fraction by putting it over 1. But when we flip that fraction, it becomes 1 over 0. And we all know that 1 over 0, division by 0, is undefined in our number system. And so what happens graphically when we divide by 0, when we flip that fraction, is we get a vertical asymptote in our graph. So everywhere where this graph is at 0, meaning every time it's at its midpoint, we're going to get a vertical asymptote in the graph. Now, notice that I'm drawing in my vertical asymptotes also with dashed lines, because asymptotes aren't a part of our graph. But they're really helpful to see because these two pieces that make up one cycle of our cosecant graph do approach those asymptotes. They approach the asymptotes. They get ever closer and closer in that direction. Wow. Okay, now these snippets that I did of this, they look like the pieces just stop, but those really have arrows on the end. They really keep going forever and ever. And so they approach those asymptotes. Now, so when we are at the midline, we get that's when we were at 0. When we flip those fractions, the flip of the graph, the cosecant graph, has asymptotes everywhere where sine was at its midpoint. Now, the top half of that curve flips up, the bottom half flips down. So I think if you're up, you're happy. And so when the up part flips up and kind of looks like a smiley face, when you're down, you're sad. So the down part flips down and kind of makes like a frowny face. But you can also just think of it as both pieces just flipping out. Okay, so they flip out from the midline. Okay, so any questions on that basic shape of a cosecant graph? So the 5 key points for a cosecant are actually asymptote at our first one, then the vertex of that smiley face, asymptote in the middle, the vertex of that frowny face, and the asymptote on the outside. Okay, so when we flip that sine function, that's what we get. And you can see the repeat of that here. If we go backwards, we have a negative cycle. It's got asymptotes on the outside and in the middle. Then it's got that vertex of the frowny face and vertex of the smiley face, okay? So that would be another cycle. If you wanted to see another cycle, could highlight it in different colors. Let's go. So there we have a second cycle. And if you needed help seeing that, then you could have just continued your sine function with the dashed line, the dashed curve, and just flipped it out. Everywhere where the sine function would be at the midline, when we flip 0, we get the 0 on bottom undefined, and we get a vertical asymptote. Then we flip the top half up for the smiley face and the bottom half down for the frowny face. And that's our function. Okay, so let's talk about where our vertical asymptotes occur here. Okay. So the numbers are super small, so I'm going to write them bigger here so you can see them. So we have an asymptote at 2 pi. We have an this is negative 2 pi. An asymptote at negative pi. An asymptote at 0. An asymptote at pi. And an asymptote at 2 pi. Okay, so where are our asymptotes happening? Where are asymptotes happening? They're happening every pi units. Can you see that? Negative 2 pi, negative 3 pi, negative 4 pi. If we kept going backwards, positive pi, positive 2 pi, positive 3 pi, positive 4 pi, if we kept going forward. So they're happening at multiples of pi. In number theory and in number systems, you're going to have to come up with a way to describe the different patterns that you want. So this is one of the first times we have to be able to describe that pattern, that it happens every pi units. Okay, so if we think of that as just multiples of pi, oh, I'm glad you made it in, Elias. Thanks for letting me know. I'll go ahead and fix your attendance real quickly. If we think of it as multiples of pi, can you think of how we could express that, how we could write that? Okay, I got that updated. So we're going to write it in set notation. So I'm going to come down here, and VA stands for vertical asymptotes. Now, vertical asymptotes are x equals equations. So I'm going to start by writing that my asymptotes happen at x equals, and there's a whole set of them. So I'm going to use curvy set brackets. Sorry, that's a little messy. X equals, and I'm going to do my curvy set brackets. And I'm going to call it the set of all k pi. So this is a lowercase k as a variable, k pi. And put a comma. That means where k is an element of the integers. So capital Z is the letter that means integers. And I'm going to close my set bracket. Okay. So x equals the set of all k pi, where k is an element of the integers. So let's talk about the symbols and what they mean for just a second. Okay, so remember I said they happen at multiples of pi? That's what k pi means. It means k times pi. A k is a multiple of pi. But we don't want anybody saying half a pi. We don't want them to multiply it by fractions. We just want them to multiply it by whole numbers. So that's why we said where k is an element of the integers. Remember, capital Z stands for the integers. And the integers is the set of all positive and negative whole numbers. So it's positive and negative whole numbers. So like -2, -1, 0, 1, 2 with ... ellipsis continuing in both directions. Okay, so the integers are all positive or negative whole numbers. Okay, so we said that k has to be an element of the integers. Questions about that? The set of all k pi where x equals the set of all k pi where k is an element of the integers. X equals because that's in a vertical line equation. And then that. Okay, once you have figured out how to describe the vertical asymptotes, the domain is very easy. So the domain is going to be all real numbers, because it keeps going forever and ever in both directions, such that, so we're going to do our straight line such that x does not equal whatever our asymptotes do equal, because it's all real numbers except for where we have asymptotes. So it's all real numbers such that x does not equal k pi, multiples of pi, where k is an element of the integers. Now that symbol, element of, It looks like a sideways U with a line in it. Okay, it doesn't look like a regular E. Okay, it looks like a sideways U with a line in it. This means is an element of. It means it belongs to the set of. Okay, so it's an element of. So when we talk about number theory and sets of numbers, element of. So the domain is almost all real numbers such that X just does not equal those values where we have asymptotes. So that was the set of all K pi, where K is an element of the integers. Jeremiah, we're going to kind of review it in the next few examples. So rather than revisiting it on this one, when we go through our next functions, you'll get to see an example of it. And at the end of class, if you still have a question about it, let me know. Okay, so what's the period of the parent function? Because a cosecant is just a reciprocal of sine, it's going to have the same period of the parent function as sine did. Sine took 2 pi units to get through a full cycle, so will cosecant. Cosecant will need 2 pi units to get through a full cycle. What's the range of cosecant? I'll help you with this one, and then on the next one, I'm going to make you guys help me with it, okay? So look at those arrows. Those are going all the way down to negative infinity. So my range starts as low as negative infinity all the way up to, okay, notice there's a break in our graph. At the vertex of this frowny face, that's where our graph stops for a while, and that's at -1. So -1, and it gets inclusive, so it gets a bracket. But there's another piece of our graph. It's not just the frowny face. We're going to union that with, where does our smiley face start? It starts down at its vertex at +1. So that's +1 inclusive, because we do hit a value of +1 all the way up to positive infinity. Those arrows are going to keep going all the way up to positive infinity. Questions on the range there? Questions on the range? From negative infinity up to -1, union with +1 up to infinity. That part in the middle is not part of the graph. It's just what we use to help us get the graph. Okay. All right. So that's our cosecant parent function. Let's try our next parent function. Okay. Identify the 5 key points of the secant graph. Okay. Remember, this looks very similar, right? This looks a lot like what our cosecant graph just looked like. Secant is the reciprocal of cosine. And just like sine and cosine can be written as phase shifts of each other, secant and cosecant can be written as phase shifts of each other. We do want to remember secant is the reciprocal of cosine. So if you're trying to see what your parent function is going to look like, we're going to start by graphing the parent function of cosine. Okay, so cosine, positive cosine starts at its maximum. So I'm going to plot there at the maximum at +1, and it has a period of 2 pi. So it goes maximum, midline, minimum, midline, maximum. And if we connect that with a dashed line, a smooth curve, that's our cosine parent function. And we're going to use that. That's one cycle of our cosine parent function there in a dashed line. It's in a dashed line because it's not part of my secant graph. I'm going to use it to get my secant graph, okay? So we said secant is the reciprocal of cosine. So what we're going to do is we're going to flip the fractions for all of our cosine values, and we're going to get our secant values. So again, when my cosine value is at 0, we make that a fraction by putting it over 1. And when we flip it, 1 over 0 is undefined. It's undefined. So everywhere where cosine was at 0, secant is going to be undefined, which generates a vertical asymptote on its graph. Okay, so everywhere where cosine is at 0, secant will be undefined, which generates a vertical asymptote. Okay, so notice at this time, we've got 2 asymptotes kind of a quarter way through the graph, a quarter way and 3/4 of the way through the graph. Okay, that's where the asymptotes happen for cosine. When my fraction is 1, let's take a look at that. When my fraction is 1, I can make it a fraction by putting it over 1. And when I flip it, it's still 1 over 1. So my next key point, my first key point for cosine is at 1, 1. Okay. When I'm at -1 for cosine, I'll change that color. When I'm at -1 for cosine, I can make that a fraction by putting it over 1. When I flip it, it's still 1 over -1, which is still at -1. That's why that next key point is in the same place that it was for cosine, okay? Our last key point is 1 over 1 also. When we flip it, it's still 1 over 1. So those stay the key points. And then we're going to flip all of the values. So we're going to just flip the whole graph. So when it's up, it flips up and makes part of that smiley face. When it's down, it flips down and makes that frowny face. When it's up, it flips up. And it really is just by flipping each individual value. And that's why I said mathematically, I think this is super cool. So let me just show you for like a couple more values. Like here, when my cosine was at 1/2, when I flip that, that becomes 2 over 1. And so that's why it jumps up to +2. Okay, and you can do that with all of the values. When you're at 1/4, it jumps up and is at 4. Okay, when you're at 3/4, it becomes 4/3. Okay, so it's really interesting to see how when you flip those fractions, it literally flips the graph like that as well. I think it's super cool. Notice for secant, we have like half of a smile, a full frowny face, and the next half of the smile. So it's not like as pretty of a picture if we jump back and take a look at our cosecant. Sorry, you probably didn't appreciate that. Okay. There, one cycle is the full smiley face and the full frowny face. But for secant, it's half a smiley face, full frowny face, the other half of the smiley face for one full cycle. But you can see another cycle graph there as well. Again, if we just continued that cosine graphing maximum, midline, minimum, midline, maximum going backwards, that would have been that cycle there. Everywhere where the cosine value is at 0, when we flip it, it becomes undefined. So we get those vertical asymptotes everywhere where cosine was at 0. -1 over 1 flipped is still -1 over 1. +1 over 1 flipped is still +1 over 1. +1 over 1 flipped is still +1 over 1. So we have those key points. And it ends up looking like, I've got to pick a color here, sorry. So we have the upward part of this half of the smiley face, the full frowny face, and half of the smiley face for that second cycle going backwards. Okay, questions about getting the graph of secant. It's just the reciprocal of cosine, so it's the flip of the graph of cosine. Okay, now let's talk about where its vertical asymptotes happen, and that'll help us get our domain. And then we'll get the range and the period of the parent function. We can do period of the parent function right now, so why don't we do that? Cosine had a parent function with a period of 2 pi. This is just the reciprocal of that, so it still needs 2 pi as well to get through a full cycle. So the period of the parent function is still 2 pi. Where do these asymptotes happen at? This time it's at -3 pi over 2, -pi over 2, pi over 2, 3 pi over 2. And we could just keep going, right? The next one would be 5 pi over 2. The next one would be 7 pi over 2. So can you describe that pattern of where the asymptotes are happening? Can you describe that pattern of where the asymptotes are happening? Good, good. That's right. They're happening at the half pi's or the pi's over 2. Now, one thing I want to point out about this is how far apart are they? So you're right, Jeremiah, they happen at the half pi's and they are still pi units apart. And so that's going to help us when we try to describe this pattern. Okay, so let's think of how we could describe this in set theory. So we know that these are vertical asymptotes, so there's still going to be x equals equations. X equals, and it's going to be the set of all because we have a whole set of them. This goes forever and ever in both directions, so there's an infinite set of them. So we have to describe them with a pattern because we can't possibly list them all, okay? So x equals the set of all, and we're going to say pi over 2 because they happen at the half pi's. Okay, so that'll get us on a half pi. As soon as I say pi over 2, we're starting at a half pi. And then we're going to say plus k pi, where k is an element of the integers. Okay, so let's talk about that. Pi over 2 plus k pi, where k is an element of the integers. Okay, the pi over 2 is going to get us to start here at our first asymptote at pi over 2. Then we're going to go forward any multiple of pi, and we'll hit another asymptote. As long as k is an element of the integers, that means if I go forward 1 pi, I hit another asymptote. If I go forward 2 pi, I hit another asymptote. If I go forward 3 pi, I hit another asymptote, because each of the asymptotes are pi units apart. K is just a variable. It's just a variable, okay? So we define k as having to be an element of the integers. So we're saying, so plus a variable multiple of pi, where that variable has to be an integer. And that's what we are doing when we say where k is an element of the integers. We're defining it as a member of the integers. Pi is the 3.14159, da, 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 da. So pi is its own number, right? So this is saying pi over 2. So start on a half pi, and then go forward any integer multiples of pi. So the fact that we chose an integer means it can be a negative whole number multiple of pi as well. So we can go plus negative 3 pi, which would take us backwards 3 pi. We can say plus negative 2 pi, which would take us backwards 2 pi. We can say plus negative pi, which would take us backwards pi. Okay, so the fact that it's an integer picks up the plus and minus options. So plus or minus multiples of pi, because that k is bumped up against the pi, so it's multiplied by the pi. 1 over 1 and negative 1 over 1, Melinda, were the values of cosine. So when you graphed your cosine parent function, so cosine goes between negative 1 and 1 with a midline at 0. The parent function does. So the first value of cosine before we flipped it was 1 over 1, and then we flipped it, okay? The second key point for cosine was at 0, which I made a fraction by putting it over 1, and then I flipped it. So that made it undefined, okay? The third value for cosine, the third key point was down at its minimum, negative 1 over 1, and when we flipped it, it was still negative 1 over 1, okay? Does that help, Melinda? We got 2 different strands of questioning going on. Okay, good. Jeremiah, so that could be a positive or negative answer. Yes, because we have an infinite number of positive asymptotes and an infinite number of negative asymptotes. And it's because the answer is infinite that we have to describe it with a pattern with set notation. Okay, let's keep going, because we're going to practice this on tangent and cotangent too, so we'll get some more practice with it. Okay, we need to describe the domain of secant, okay? So secant goes forever and ever in both directions, so it's almost all real numbers. So we're going to say all real numbers such that x does not equal, we have this infinite set of asymptotes that we have to pull out. So it's all real numbers such that x does not equal, and this is where you just match your notation that you used for defining the vertical asymptotes. So x does not equal pi over 2 plus k pi, where k is an element of the integers. Where k is an element of the integers. Okay, now I'm going to help you take your stress down a notch now. I'm not sure if I should tell you this today or if I should tell you it next time when we're reviewing, but I'm going to tell you it today. Just take your stress down a notch. It's important for you to start developing a sense of these number sets and how to define patterns, okay? It's an intelligence test. Like if you take the Mensa test to see if you're a genius, they'll have you do pattern recognition, okay? So it's really important to start working on this. You'll do it in number theory when you get to college. But because we're only doing 1 day of this and we're testing next time, we are not going to make you use this number set definition. We won't make you do this, but I do want you to try to stay with me and try to understand it and follow the logic of it. I want you to build that ability to define an infinite set with a pattern, okay? So I don't want you to stress about it. You won't have to do it on the test next time, but I do want you to work to try to understand it, okay? All right, so what's the range? What's the range of this function? Okay, so let me have one of you guys try to help me with the range. Jeremiah, what's the range going to be for this function? I've got y values starting as low as what?
Negative infinity.
All the way up to?
-1.
Inclusive or non-inclusive?
Not
Sorry.
inclusive.
It actually is inclusive. We actually do hit -1. That's a closed circle at -1, which means we do hit it. Okay. Union with what?
Inclusive 1 to infinity.
Perfect. Exactly right. Okay. And infinity is always non-inclusive. So that's exactly right. Good job. Okay. We've got that break in the graph in the middle. That's why that's all dashed lines in the middle. We use the cosine function to help us get the graph of secant, but it's not part of the graph itself. Any questions for me on secant? 2 graphs down, 2 to go. Okay, let's try the next ones. By the way, on the test for this next one, well, I won't tell you that yet. Let's get through our notes and examples. Okay, all right. Identify the 5 key points of the graph of tangent. Okay, so take a look at that graph first before, and let's talk about the period of the parent function here. So without talking about specific values or anything, how long does it take to see everything that tangent has to show you before it just starts repeating? What does it look like the period is of tangent? How long does it take to get to see one full cycle? And I'm looking for answers from anybody who thinks they can see. How long is it before tangent just starts repeating itself and you're seeing something that you've already seen before? That's right, Melinda. It's pi units. Very nice, Travis. Exactly. It's pi units. If we start here at 0, and that's where the parent function is going to start, right here at its midline at 0. Okay. We see this upward swing. So I'll highlight it kind of here to draw your attention to it. So we see this upward swing of tangent. And by the way, there is an asymptote there that, of course, we don't graph asymptotes normally. Like you don't see them on a graph because they're not part of the graph, but we like to draw them in so we can tell what's going on there. So that upward swing of tangent is approaching that asymptote vertically. And then we have this section of tangent coming from the other side. From the other side of the asymptote back up to the midline. Okay. And that's one full cycle of tangent. Now, it may look weird to split it like that, but it has to do with us just starting at 0 and moving forward until we've seen everything that tangent has to show us. So tangent's at the midline at 0. It's at an asymptote at pi over 2. And it's back to the midline at pi. And it's shown us everything that it has to show us. Okay. So if you wanted to see another cycle of pi, you could draw another one going forward. So I would draw in my asymptote there. And that next cycle would start at the midline and go up, approaching the asymptote, come from the other side of the asymptote back to the midline. And that would be another cycle of tangent. Okay. We can draw one on the other side. We draw in that asymptote. On the negative side, okay, you can have a cycle that starts at the midline going up towards the asymptote, starts from the other side of the asymptote back towards the midline. Okay, so each period of tangent only needs pi units. Only needs pi units. Now, this is going to be important when we're looking for the period of an equation that has transformations in it. Because Ms. Weaver always tells you to find the period, it's period of the parent function divided by b. So when we're talking about tangent, it's going to be pi divided by b as opposed to 2 pi, which it was for sine and cosine all the time. For secant and cosecant, it'll still be 2 pi divided by b because those came from sine and cosine functions. But when we do tangent, it's going to be pi divided by b when we're looking for the period. Okay, because the parent function has a period of pi units. Okay, so where did the asymptotes happen here? Help me with where the asymptotes are happening at. I'll write it a little bit bigger. I'll sketch in that next one. We'd have another asymptote here at -3 pi over 2. That cycle starting there. Okay, so there would be that cycle. So our asymptotes are happening at -3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2. Okay, so where are they happening? That should look familiar. They're happening on the half pies. That's right, Morgan. They're happening on the pi over 2s, the half pies. Okay, so how did we describe the set of all asymptotes that are happening on the half pies? How did we describe that? Well, they're vertical asymptotes, so they're x equals equations. So we said x equals the set of all, so we're using set brackets, pi over 2 to get us on the half pies. And then remember, it's just pi units from asymptote to asymptote. So every pi units, I have another asymptote. So we're going to say pi over 2 plus k pi plus an integer multiple of pi. And so we're going to define k as an element of the integers. Close the set bracket, okay? So x equals the set of all pi over 2 plus k pi, where k is an element of the integers. Okay. Questions about that? It's our second time to see it. Hopefully we're starting to understand it a little bit more. Okay, so what would my domain be then? Okay, anybody think they can try that? I'm not going to put you on the spot here, but if you think you can do it, let's unmute and describe what's the domain going to be. It's everywhere where my vertical asymptotes are not. So how are we going to describe that? I believe somebody can do it. I know one of you can. Who thinks you can do it? You may not want to say the words right, like it's a little stressful, right? But we are a community of learners. We're here to support you. No takers this time? Okay, I'll help you with it. Okay. It's going to be all real numbers because it keeps going forever and ever in both directions, such that x does not equal whatever our asymptotes did equal. Okay, so we already have our asymptotes over there, so such that x does not equal the set of all pi over 2 plus k pi, where k is an element of the integers. Okay, so as long as we start at a half pi and go forward an integer multiple of pi or backwards an integer multiple of pi, we'll hit another asymptote. So it's all the numbers except for those. The domain is all the numbers except for those. Okay, what about my range? I see a couple of you have already filled in your range there, so you knew it and weren't waiting for me on that part. Let me go see. Audrey, what was our range for tangent?
All real numbers.
You got it. That's going all the way down to negative infinity and all the way up to positive infinity with no break in those graphs. Very nice. Okay. All right. Any questions for me on tangent? Now, before I flip the screen to the next screen for cotangent, okay, what do we know about tangent and cotangent? Tangent and cotangent are reciprocals. That's right. They are reciprocals. So cotangent is going to be the flip of the tangent graph in the same way that cosecant was the flip of the sine graph and secant was the flip of the cosine graph. That's what I think is super cool. The reciprocal fractions generate reciprocal graphs or flips of the graphs. But let's see what that's going to look like when we're talking about cotangent. So let's go take a look at cotangent. Okay, this is the graph of cotangent. Now, we don't have to graph tangent and then flip it. We're going to be able to just memorize it, thinking about what these differences were. Remember that tangent started at the midline at 0. So tangent started at 0 over 1. So tangent was here at 0 over 1. And when we flip that, that becomes 1 over 0. And we know division by 0 is undefined in our number system. So everywhere that tangent was at 0, cotangent is going to have a vertical asymptote. So tangent started at 0 and pi units later ended at 0. So when tangent was 0, cotangent is going to have another vertical asymptote. Cotangent will also have a parent function with a period of pi units because it's just a flip or the reciprocal of tangent. And so if tangent only needed pi units to finish a full cycle, cotangent will only need pi units to finish a full cycle. So both tangent and cotangent have parent functions with a period of pi units All 4 other trig functions have parent functions with periods of 2 pi. Okay. Now, tangent had an asymptote in the middle. Tangent had an asymptote in the middle. And I should have said that. I'm going to jump back to that slide, so I apologize. I forgot to tell you guys how I remember this one. Okay. So this pink cycle we were looking at was our first cycle of tangent, and it had the asymptote in the middle. So we say tan ASI in the middle. And I know that sounds a little dangerous, tan ASI in the middle. ASI stands for asymptotes. But that phrase, tan ASI in the middle, will help us keep tangent and cotangent, how to tell them apart. Tan ASI in the middle, tangent has the asymptote in the middle of its cycle. So we have the little half swing up, asymptote, the other half swing up. The other thing I want to point out here is that tangent is an increasing function. If you take a look at the graph, if you put your finger on the graph as you move left to right, it's always increasing, which sounds funny because you see the arrows going both directions, but put your finger on the graph. It's increasing for that first section, then we jump to the other side of the asymptote and we're increasing again all the way up to the next asymptote. Then we're increasing again all the way up to the next asymptote, then increasing again all the way up to the next asymptote, then increasing again. Okay, so tangent is always increasing. It's only an increasing function. It's an increasing function. So when we flip it to get cotangent, what do you think about cotangent? If tangent's always increasing and we flip it, what is going to be true about cotangent? Cotangent is always decreasing. Cotangent is going to be a decreasing function. It's going to be a decreasing function, meaning if you put your finger on the graph moving left to right, the y values are always decreasing. Okay, so the y values are always decreasing. Next piece, decreasing. Next piece, decreasing. Next piece, decreasing. So cotangent is a decreasing function. But let's finish getting our one cycle graphed. So where tan ASI was in the middle, tangent's asymptote was in the middle. So that was because it was undefined. When we flip that, we get back to 0. So we get back to 0 here for our key. Where tangent was undefined, had a vertical asymptote, cotangent will be at 0. Okay. Now, this is also another thing I really like that I think is super cool about tangent and cotangent. We're going to use that MAPI process to graph them too. You'll see it in just a second. We'll do it in a second. But we don't really have an amplitude with tangent and cotangent because they go all the way up to infinity and negative infinity. But that same idea of amplitude going from the midline up that many units and midline down that many units still gets us to a key point. So for the tangent function, if I were to write that parent function, y equals, cotangent rather, cotangent of x, then the amplitude is 1. Only we said it's not really an amplitude. But if we go from the midline up 1 unit, up the amplitude to 1, and from the midline down 1 unit, so down the amplitude to 1, we will still get the next key point. So our midline is still here at 0. And we can go midline up to a key point and midline down to a key point. So the 5 key points for tangent are asymptote, up the amplitude, midline, down the amplitude, asymptote. Okay. So if we highlight that cycle, the other thing that's nice about cotangent, if it's for cotangent, it is one continuous piece of that. Tangent and cotangent look very similar. Okay, the parent function for one cycle of cotangent is the complete pretty piece. But tan ASI in the middle, tangent has the asymptote in the middle, so tangent we only get half of the upswing, asymptote half of the downswing. Okay. Now the other way I remember this is if you write cotangent of x, if we're looking at the parent function cotangent of x, cotangent has OT, cotangent, which means the asymptotes, ASIs, on the outside, outside. So OT, outside. Asymptotes are on the outside for cotangent. So cotangent, ASI's on the outside. Okay, now you can see those other cycles. If you repeated them, every pi units, we have another asymptote. And that would be amplitude, midline, amplitude. Okay, so that would be the next cycle. I might undo that. We can go back, see another asymptote. It'd be there, there, and there for those key points. And it's always decreasing, right? So it's always coming down as we trace that cycle, okay? So we could do another one, have the asymptote on the outside. It'd be there, there, there. We connect it. Okay, so that's what cotangent is going to look like. So how are you going to tell cotangent and tangent apart when you're like given an answer choice, you're trying to match graphs, and you see, and they look very similar. They look very similar. Okay, stay with me. I know you're going to think that this doesn't really look like it. It's not hard, but it doesn't really, you're going to say, Ms. Weaver, that does not look like it. Okay, and I'll just show you, it looks more like it than the other graph does. Okay, so I say the graph of cotangent kind of looks like the capital letter C here, kind of looks like it could be a C there, and you're like, no, Ms. Weaver, it really doesn't. But let's go look at tangent. Let's go back and look at tangent. Let me get the screen to go back to go with it, sorry, okay. That definitely doesn't look like a C because the continuous part of it's on the wrong side, okay. So let's go look at cotangent again. Okay, so can you see how cotangent kind of, not really, but enough that we can use it to help us remember. Cotangent kind of looks like a C there. So that's the one that's cotangent as opposed to that one that's tangent. So cotangent is decreasing, tangent is increasing. Cotangent kind of looks like a C, tangent doesn't look like a C at all, okay? So that's how I remember it. I'm just sharing my best memory cues. You guys can use whatever memory cues you use to help you tell them apart. Okay, there's more than one way to memorize something, that's for sure. Okay, so what about where the asymptotes happen here? Let's look at our asymptotes for this one. We've got an asymptote at negative 2 pi, at negative pi, at 0, at pi, and at 2 pi. So how can we describe, and remember this keeps going forever and ever in both directions, okay? So how can we describe where these asymptotes, these vertical asymptotes are happening? Anybody think they got it? Anybody ready to try it? They're happening every pi units, okay? So how did we describe that every pi units we have an asymptote? How do we describe that? They happen every pi units, okay? They're vertical asymptotes, so they're going to be x equals equations. So we said x equals the set of all. Anybody want to try it? Okay, I see some of you wrote it, so I'm really proud of you for writing it. You didn't want to say it, maybe saying it's more intimidating, but I see some of you already have it correctly described there in your pair deck, so good job. It's the set of all k pi, you're right, the set of all k pi, where k is an element of the integers. We're saying it's multiples of pi, where that multiple has to be a positive or negative whole number. That's what integers means, is positive and negative whole numbers. So it's any positive or negative whole multiple of pi, okay? So the set of all k pi where k is an element of the integers, okay? Once we've defined our vertical asymptotes, then it's so easy to find the domain. It's going to be all real numbers because it keeps going forever and ever in both directions, such that x does not equal, the only real numbers that aren't included are where we have the asymptotes. So those asymptotes happened the set of all k pi, where k is an element of the integers. Questions for me about that? Wherever there's an asymptote, that's not part of the domain. So the domain is all real numbers except for the asymptotes. So all real numbers such that x does not equal the set of all k pi, where k is an element of the integers. Okay, what about my range on this one? That's not such a hard question. What about my range on this one? All together?
All real numbers.
You got it. It's all real numbers. It's all real numbers. Okay, questions for me on cotangent. Questions for me on cotangent. Okay, you can always go back and watch Mr. B's videos, okay? So you can refresh on this a little bit. That's all he pretty much did on the video notes was talk about the parent functions, and he literally pulled the values from the unit circle to get those values, okay? So just like that's what we did to get the graphs of sine and cosine, we just plotted the points from the unit circle, and that's what we do to get these as well. But we don't want to have to go back to the unit circle and plot all these forever and go around and around the unit circle forever. So if we can memorize what the parent function one cycle looks like, then we can just repeat it over and over in both directions. Okay? All right, so let's do some more problems. Okay, so now we have some graphs, and they just have the same transformation rules as all the other trig functions, and it says use MAPI to graph one cycle. So what Mr. B said in the video notes, if we want to graph cosecant, we need its reciprocal sine. Okay, so do you remember your trig reciprocals? The reciprocal of cosecant is sine. So what we're going to do is we're going to use a dashed line to graph y equals the exact same equation, but changing out cosecant for sine. So 5 sine 1/2 theta minus pi minus 3. So we're going to graph that with a dashed line, and then we're going to flip it out to get the cosecant graph. So let's do that. So we're going to use MAPI, M-A-P-P-I. Okay, and can you help me with this first one? Aditi, what's my midline here? What's my midline? Aditi, what's the midline? And we should be really solid at this. We just took a test on it. Are you with us, Aditi, or should I change your attendance? Okay, so then you need to answer. Okay, even if you're not sure, you can say not sure. Midline is our constant there at the end. That's our D value. So our midline is at -3, so down 3. What's our amplitude? It's our A value. A is for amplitude. That's going to be +5. So I'm going to put my x-axis about right there. Okay, so -3 is going to be my midline. Okay, so I'll draw in my midline. My amplitude is 5, so I'm going to go up 5 to my maximum at +2 and down 5 to my minimum at -8. And I'm going to draw those a little closer in so that I have more room to flip out my graph. Okay, so I'm going to say up 5 to 2 and down 5 to -8. Okay, my phase shift here is pi units. So that means I'm coming forward pi units on the x-axis. Okay, my period is period of the parent function, which for cosecant is, and sine and cosecant is 2 pi. We're graphing sine right now, so it's 2 pi, divided by the b value, which is 1/2. So divided by 1/2. To divide by a fraction, we multiply by its reciprocal, so that's multiplied by 2/1. So my period is 4 pi. To get the interval that we're going to count by, we're going to grab that period we just found. This is review for all of you that are still finishing up your test, right? We're going to do 4 pi divided by 4. We're going to take that and divide it by 4. 4/4 cancels. That gives me an interval of pi. I'm going to mark out 4 equally spaced points, 1, 2, 3, 4, and we're counting by pi. So starting at pi, counting by pi. So my next key points are going to be 2 pi, 3 pi, 4 pi, 5 pi. Okay, so I started at pi, 4 pi units later, I'm at the end of my cycle. Okay, we've got our 3 key y values, 5 key x values. We are ready to go. With a dashed line, we're graphing a positive sine function. So positive sine function starts at the midline, like all sine functions do. Then it goes to the maximum, then midline, then minimum, then midline. Connecting that with a dashed line, because it's not part of our curve, it's just going to help us find our graph. Okay, so dashed line because it's not part of our actual graph that we're looking for. Okay, that's one cycle of 5 sine 1/2 theta minus pi minus 3. Questions on that? Okay, now we're ready to graph cosecant. So we're going to flip it. Everywhere where sine is at its midline, cosecant is going to have a vertical asymptote. Cosecant will have a vertical asymptote. Everywhere where sine was at its midline, cosecant will have a vertical asymptote. Then we're going to grab that top piece and flip that up like our smiley face. And we're going to grab that bottom point and flip it down like a frowny face. Okay. And the blue graph is my actual graph of one cycle of y equals 5 cosecant 1/2 theta minus pi minus 3. Okay. So the graphing it is really not too bad. It's just one extra step. You graph sine with a dashed line. Then everywhere it's at the midline, you put an asymptote and you flip the pieces, the top piece up and the bottom piece down. Questions for me about that? Okay. Now, for the interest of time, we're going to jump and try a tangent and cotangent graph real quickly. Cosecant and secant, cosine generates secant, and it's just the same idea as doing sine. So I don't think we need to practice one of those. So for the sake of time, we're going to move forward. Okay, Jeremiah, thanks for notifying the attendance office. Okay, let's try another one. Okay, so if we want to graph MAPI, use MAPI to graph 2 cycles of tangent. Let's try 2 cycles this time. So I'm going to do MAPI. Remember, when it asks for 2 cycles, we just graph 1 cycle and then we'll graph another one. Okay, so we're going to graph 1 cycle. Midline here is +4 and my amplitude is 3. So I'm going to put my x-axis a little bit lower this time. So my midline's at 4. My amplitude is 3, so I'm going to go up 3 to 7. Change colors. Up 3 to 7 and down 3 to 1. The phase shift here is pi/2, so that's going to get me my starting point at pi/2. So on the x-axis, I'm going to mark pi/2. And I have a suggestion for you guys. When you're graphing a tangent and cotangent, remember their period is half as big as the period of sine and cosine. Put your points closer together. It will make these graphs easier to graph. In the x direction, put your 5 key points closer together. So the period is period of the parent function, which for tangent is pi units, right? Not 2 pi anymore. For tangent and cotangent, it's pi units. Divided by our b value. There's a coefficient of 1 in front of x, so it's just pi divided by 1. So my period is still going to be pi units. Grab that period, bring it down here and divide it into 4 equal parts. So my interval is just pi divided by 4. So I'm starting at pi/2, counting by pi/4. So I'm going to go ahead and make those 1, 2, 3, 4 equally spaced points. I tried to put them closer together just to make it easier to graph. So 4 equally spaced points. We said pi/2 is 2 pi/4. So if I add pi/4, that'll be 3 pi/4. 4 pi/4 is a whole pi. 5 pi/4. 6 pi/4 simplifies to 3 pi/2. Okay, so we're ready to graph tangent. So tell me what you remember about tangent. We said tan assy in the middle. So at our middle key point, we're going to have an asymptote. So tan assy in the middle. So I'm going to start by drawing the asymptote in the middle. It starts and ends at the midline. Okay, it starts where it ends. They have to start and end in the same place to be one full cycle. So it starts and ends at the midline. Now, because it's an increasing function, we go up the amplitude to a key point. So that's our first piece of it. And then we come down for that next one. So coming from the asymptote through that key point back to the midline. Let me see if I can make that a little smoother. And that is 1 cycle of tangent. Questions for me about that? That's 1 cycle. They said they want 2 cycles, so I'm going to draw 4 more key points. 1, 2, 3, 4. Still counting by pi/4. So 3 pi over 2 was 6 pi over 4. So my next one is 7 pi over 4. 8 pi over 4 simplifies to 2 pi. 9 pi over 4. 10 pi over 4 simplifies to 5 pi over 2. Okay, so what do we know about tangent? We say tan assy in the middle. So at that middle key point, I'm going to put an asymptote. It starts and ends at the midline. Tangent's an increasing function, so that next key point is going to be up the amplitude. And then down the amplitude will be our other key point, coming from that asymptote, increasing up back to the midline. That's 2 cycles of tangent. Questions for me about that? Okay, we got 3 minutes to see what we can get done. I wanted to show you a cotangent cycle real quickly, so let's do that using MAPI. The rest of it is just the same transformation rules that we talked about with sine and cosine. So your assignment today, if you noticed on the agenda, the assignment today is the study guide. Okay, so there's no Delta Math assignment tonight. The assignment is the study guide. And this time, because that's our only assignment, the study guide is a minor summative. So it's going in the gradebook for a grade. So you have to get the study guide done between now and when I see you on Friday for the test. Okay, don't stress too much because we're going to start by reviewing for the first half of class again. Okay, so we'll get a little more solid on this. But let's make sure we can get the basic idea of graphing. And this is where I was going to tell you. You guys won't have to graph by hand on the test. You'll just have to match graphs to equations and answer questions about equations, okay? So it'll just be the transformation questions, but we want to make sure we can do it. So midline on this one is at -1, amplitude is 1. So this one's going to be down. I'll put my x-axis just a little bit up. Midline's at -1. Amplitude is 1, so I'm going to go up 1 to 0 and down 1 to -2. Phase shift is 0. There's 0 phase shift this time, so my first key x value is also 0. Period is period of the parent function divided by b. So what's my parent function's period for cotangent altogether? Oh, that was no response on altogether. How did we get no response on altogether? Tangent and cotangent have a parent function with a period of pi units. You've got your notes right there. You can go back and look at them, okay? So that's going to be pi units divided by our b value of 1/3. Dividing by 1/3 is the same as multiplying by 3/1. So that's going to be 3 pi. What do I do with the period when I find it? I bring it down and divide it into 4 equal parts to get my interval. So 3 pi divided by 4 is what we're counting by. So we're starting at 0, counting by 3 pi over 4. So I'm going to do 1, 2, 3, 4 equally spaced points. Again, I tried to keep them closer together to make it easier to draw the shape. So starting at 0, we'll get 3 pi over 4. 6 pi over 4, which simplifies to 3 pi over 2. Nine pi over 4. That's really messy. 12 pi over 4, which simplifies to 6 pi. Wait, no, 12 pi over 4 simplifies to 3 pi. Self-correction, it's important, right? 12 divided by 4 is 3, so that'll be 3 pi. Okay, I went ahead and simplified as I went, but you could have just said 3 pi over 4, 6 pi over 4, 9 pi over 4, 12 pi over 4, and then came back and simplified in the second step, okay? Either way is okay. So what do we know about cotangent? Think about that OT. OT means outside. That has asymptotes on the outside. So I'm going to have an asymptote at my first key point and at my last key point. which means it's at the midline in the middle. Remember, it's the flip of cotangent. So it's the flip of tangent. So tangent had AC in the middle. So cotangent's at the midline in the middle. Okay. Then it's a decreasing function. Oh, sorry, I'm not at my midline there. Let me fix that spot. Here's my midline down here. So I'm right there. Okay. And then we go up the amplitude for a key point and down the amplitude for a key point. Cotangent is decreasing the whole time. So that's one decreasing cycle of cotangent. Remember I said it kind of looks like a capital C for cotangent? Okay, kind of looks like a capital C for cotangent. Okay. Questions for me on graphing a period of cotangent?